A ring of plasma, hotter than the center of the sun, held in a magnetic cage, inside a machine in eastern China. And on January 1st, 2026, that machine did something every fusion textbook said was impossible. It pushed the plasma past a limit that had stood for almost 40 years, a limit named after the American physicist who defined it. China broke an American's law, and almost nobody outside of physics noticed. For 50 years, there's been a running joke about fusion energy. It's always 30 years away, and it always will be. The joke stuck because it was mostly true. The science worked, the engineering didn't. Governments poured tens of billions into fusion research. France is building a reactor called ITER, International, decades late, billions over budget, still not running. Meanwhile, in a lab in Hefei, China, a machine called EAST was quietly setting records. And on the first day of 2026, it didn't just set a record, it broke a rule. What EAST actually is, EAST stands for Experimental Advanced Superconducting Tokamak. It's a donut-shaped machine, about the size of a small house, sitting at the Institute of Plasma Physics in Hefei. Built between 2000 and 2006, operating ever since. The design is called a tokamak, a Russian acronym for a magnetic chamber. The idea is simple, even if the engineering isn't. Take hydrogen gas, heat it until it becomes plasma, the fourth state of matter, hotter than the sun's core. Then trap that plasma in a magnetic field shaped like a donut so it never touches the walls. If you hold it hot enough, dense enough, long enough, the hydrogen atoms smash together. They fuse, and when they fuse, they release energy. Clean, limitless, no carbon, no radioactive waste that lasts for millennia. That's the promise. That's why people have been chasing it for 70 years. The problem is that holding a cloud of plasma at 100 million degrees inside a metal donut is like trying to hold a hurricane in a glass jar. The plasma wants to escape. It wants to collapse. It wants to tear itself apart. And for decades, there was one number that kept everyone's ambitions in check. The Greenwald limit. Why this limit mattered? In 1988, an American physicist named Martin Greenwald was studying tokamak data from machines around the world. He noticed a pattern. There was a ceiling, a specific plasma density that no tokamak seemed able to push past. Above it, the plasma would destabilize. It would collapse. The reaction would die. He wrote it up as an empirical formula. Not a law of physics, more of an observed limit. A ceiling that every machine had hit. The formula was simple. The density cap was proportional to the plasma current divided by the cross-section of the donut. You could calculate it on a napkin. For almost 40 years, that napkin calc defined the upper boundary of what anyone thought a tokamak could do. Every reactor design in the world, including ITER, the multi-billion-dollar international project in France, was built around staying under the Greenwald limit. And the reason it mattered so much was this: density is power. The denser the plasma, the more hydrogen atoms you have in a given space. The more atoms, the more collisions. The more collisions, the more fusion reactions. The more reactions, the more energy. Greenwald was the ceiling on how much power a fusion reactor could ever produce. If you couldn't push past it, fusion would always be a lab experiment, never a power plant. For 38 years, no one pushed past it. Then China did. On January 1st, 2026, a team working on EAST published results in the journal Science Advances. They had run stable plasmas at 1.3 to 1.65 times the Greenwald limit. Not 10% over, not 20%, up to 65% beyond a ceiling that had stood since the Reagan administration. And the plasma didn't collapse. It stayed stable. The technique they used has an unglamorous name: ECRH, Assisted Ohmic Startup. Electron cyclotron resonance heating, basically hitting the plasma with focused microwaves at the very start of the discharge, in a way that changes how the plasma forms and stabilizes before the density gets too high. The result was that East entered what the team called a density-free regime, a state where the old limit simply didn't apply. This wasn't a marginal improvement. This was the removal of a constraint that had shaped every fusion reactor design for 4 decades. The record of 1,066 seconds nobody mentions. But here's the part most coverage missed. The Greenwald breakthrough wasn't a one-off. A year earlier, in January 2025, East set a different record. It maintained a high confinement plasma for 1,066 seconds, roughly 17.5 minutes. The previous record was 403 seconds, set by the same machine. In 1 year, China tripled its own record for how long a tokamak could hold a stable plasma. And almost no one outside fusion physics even heard about it. 2 records, 2 years. Same machine. One for how long it could hold the plasma. One for how dense it could make the plasma. Both are the numbers that decide whether fusion is a science project or a power source. Why density and duration are the whole game. Here's why those 2 numbers matter more than the headline artificial sun suggests. Fusion needs 3 things at once: temperature, density, and time. You need the plasma hot enough that the atoms have enough energy to fuse. That's mostly a solved problem. We can heat plasma to 100 million degrees. You need the plasma dense enough that the atoms actually collide often enough to produce meaningful power. That's the Greenwald problem. For 38 years, the ceiling. And you need to hold it all together long enough for the reactions to sustain themselves. That's the duration problem. A plasma that lives for a second is a flash. A plasma that lives for 17 minutes is something else. East is the only machine on Earth that has pushed both of the hard numbers, density and duration, past where anyone thought they could go. Temperature was never the bottleneck. Density and time were. And those are the 2 China just moved. The Hefei machine versus the France mega project. Now put this in context. Because East doesn't exist in a vacuum, it exists alongside the most expensive science experiment in human history. ITER, the International Thermonuclear Experimental Reactor, under construction in Cadarache, southern France, since 2010. ITER is a 35-country collaboration. China is part of it. So is the United States, the EU, Russia, Japan, Korea, India. ITER was supposed to start operating in 2016, then 2025. Now the first plasma is hoped for sometime around 2034. The full deuterium-tritium campaigns, the actual fusion experiments, won't happen until the 2040s. The budget started at 5 billion euros. It's now estimated at 20 billion or more. No one really knows the final number. ITER is a masterpiece of international collaboration. It's also a case study in what happens when 35 countries have to agree on a budget, a timeline, and a design. East is the opposite. One machine, one country, one institute. Operating since 2006. East is smaller than ITER will be, much smaller. But it's running. Now, today. And it's the testbed for technologies that ITER will eventually use. China isn't waiting for ITER. China is building the cheaper, faster version in Hefei and using it to break records. ITER hasn't even tried to set yet. The next machine, CFETR. And here's where the story gets bigger. Because East is the research machine. China's next step is a reactor called CFETR, China Fusion Engineering Test Reactor. CFETR is designed to do what East can't, actually demonstrate a fusion power plant, not just a physics experiment. The roadmap is public. Phase 1. Steady-state operation and tritium self-sufficiency, meaning the reactor makes its own fuel, a critical step no machine has achieved yet. Phase 2. Upgrade to 1 gigawatt of fusion power. The Chinese roadmap puts CFETR construction starting by the late 2020s. Operation in the 2030s, a prototype fusion power plant by 2050 to 2060. That timeline looks aggressive. It also looked aggressive when China announced its high-speed rail plan in 2003, and they hit it. The 582-ton magnet, the detail nobody mentions. Here's a detail almost no one reported. Outside of fusion trade press. In July 2026, China completed final tests on the world's largest superconducting fusion magnet, a 582-ton coil, built entirely with domestic supply chains, 582 tons. That's the weight of a fully loaded 747. The magnet is the heart of a tokamak. It's what generates the magnetic field that holds the plasma. A bigger, stronger magnet means a bigger, more powerful reactor. And this one was built with no foreign components, no German supplier, no American contractor, no Japanese technology transfer. The CR450 wasn't the only Chinese flagship project with fully independent IEEP this year. The patent race, the number that tells the real story. There's a statistic that doesn't get enough attention. Since 2015, China has approved more fusion-related patents than any other country in the world. Not filed. Approved. More than the United States. More than Japan. More than the European Union combined. Patents are a lagging indicator. They tell you what people were working on 3 to 5 years ago. China's fusion patent surge started a decade ago. The green-walled breakthrough is what that decade of investment looks like when it finally pays off. In 2015, China was a follower in fusion. In 2026, China is the country breaking the limits. Why this matters beyond physics. Now, here's why this isn't just a science story. Fusion is the holy grail of energy. Clean, limitless, no carbon, no long-lived radioactive waste, no fuel that runs out, the hydrogen comes from seawater. Whoever cracks fusion first doesn't just solve climate change, they redefine geopolitical power. The country that builds the first working fusion power plant becomes the Saudi Arabia of the 22nd century. Except instead of pumping oil from the ground, they're selling the technology that makes oil obsolete. The United States knows this. In 2025, the US Department of Energy released a report acknowledging that the American lead in fusion is narrowing and that China is closing the gap faster than expected. CNBC ran a headline in March 2025. The US is falling behind China in nuclear fusion, needed to power AI. The AI angle is the new wrinkle. The biggest tech companies in the world, Microsoft, Google, Amazon, Meta, are all racing to build gigawatt-scale data centers for AI. They're hitting the limits of what the power grid can supply. Fusion is the only energy source that could, in theory, power the AI boom without melting the planet. The country that controls fusion controls the energy backbone of the AI economy. China knows this. The United States knows this. The difference is that one of them is breaking the limits right now, and the other is publishing reports about how fast it's falling behind. The 30 years away joke, and why it might finally be wrong. For 50 years, the joke was the same. Fusion is 30 years away. and it always will be. The joke worked because every prediction about when fusion would become practical turned out to be wrong. Always later, always more expensive, always another limit to break. Here's what's different now. The Greenwald limit was the single most cited reason that fusion would never scale to a power plant. It was the constraint that made every serious reactor design, including ITER, stay conservative on density. That constraint is gone. Not in theory, in experiment, in a machine that's running in Hefei today. The 30-year joke might still hold. CFETR could be delayed. The economics could fail. Tritium self-sufficiency could prove harder than expected. 100 things could go wrong between a record in a lab and a power plant on a grid. But for the first time in 50 years, the direction of the timeline has changed. Fusion is no longer always moving away. It's moving towards something. And the country moving fastest is the one nobody was watching. A ring of plasma, hotter than the sun's core, held in a magnetic cage in Hefei, China, just broke a 38-year-old limit that every fusion reactor in the world was built to respect. It's not a power plant yet. It might not be for another 20 years, but the limit that said it could never be one, that limit is gone. For 50 years, fusion was a promise that never came true. The question isn't whether fusion is real. The physics was never in doubt. The question is, who builds the first one that works? And right now, the answer to that question is not the country everyone expected. If this is the kind of story the news buries, hit subscribe. We're building this channel to cover exactly the stuff that should be on your radar. New videos weekly.